Hello everyone, my name is Tiago. Welcome to Code Tab. In this series of videos, we are solving very interesting algorithm problems that we find on the internet. And today we are solving problem number 18 from Project Euler.net. Hold on to your chairs because this is a very interesting problem and a very important problem here on Project Euler. So let's go through it. The name of the problem is maximum path sum number 1. And the description reads, by starting at the top of the triangle below and moving to adjacent numbers on the row below, the maximum total from the top to the bottom is 23. So we have this little triangle here and this highlighted path, and it says that 3 plus 7 plus 4 plus 9 equal to 23. Then they states the following: find the maximum total from the top to the bottom of the triangle below. So they give us a bigger triangle to solve. They also put a side note here that there are only 16,000 and so routes. It is possible to solve this problem by brute force, by trying every route. However, the other problem, number 67, is the same challenge, but with a triangle that contains 100 rows and cannot be solved by brute force. So if we could solve this by brute force, but I will not do so. I will already go for the clever method that they mentioned here. And then we can solve problem number 18 and problem 67 all together, right? This problem, again, brings us back to the dynamic programming solutions, right? And if you remember well from problem number 15 that we talked about dynamic programming. So dynamic programming is a technique to solve complex problems by breaking them down into smaller problems. Not every problem you can solve with dynamic programming. And there are two characteristics that helps us to if dynamic programming is the suitable solution to your problem. And one of them here is very clear in this problem number 18, which is the optimal substructure, which is this structure that the solution to the main problem must come from combining solutions of smaller problems. So you can break the problem into smaller parts, solve smaller parts, and then combine it to the bigger problem. And we can do this by simply observing at this matrix here, right? So the solution to find the max sum path from the top to the bottom is given by finding the sum to smaller triangles within this bigger triangle here. So if we imagine this bigger triangle here, and the solution to the bigger triangle depends on the solution to the triangle up to the third row, which in turn depends to the solution up to the triangle of the second row, which in turn depends on the solution of the unit triangle, which is just 3, right? So if we are able to start from the top to the bottom, solving the smaller triangles first, and then solving the bigger triangles, we should solve this problem, right? So we can apply what we call the bottom-up dynamic programming solution. How would that look like? So we can represent that triangle in this way as a matrix, right? So it doesn't matter if the triangles are like normal or if it's a rectangle triangle like this. They should solve in the same way, right? The problem states that only adjacent numbers can be combined. So we always look into the adjacent numbers upwards, right? So for example, 7, we look at 3, and 4, we also look at 3, and then we sum them up. Right, so we sum them up and then we check which one is like the largest route at that moment, right? So 3 plus 7 gives us 10, 3 plus 4 gives us 7. So the partial solution up to row number 2 is 10 and 7, right? And we know that the solution up to number 3 is going through this cell here in this matrix, right? We can do this consecutively. So in row number 3, we sum 10 plus 2 gives us 12. And then in this row in the middle, we need to check both adjacent numbers. So up and left, right? So in this case, we need to check what is the maximum sum here. So 10 plus 4 gives us 14, plus 7 plus 4 just gives us 11. So the number that we should write in this cell here must come from 10, which is 14. Similarly, we check 6. 6, we don't have an adjacent number above, so we just check it to the left, right? And that just gives us 13, right? So the path up to row number 3 is going through the cell, this route here, right? Again, we can check then the last row. the last row, then we just check the first number. We just check above because checking to the right doesn't make sense. We don't check to the right, just to the left, right? So 12 plus 8 gives us 20 here. And then in this cell here, we need to check the maximum. What is the maximum here? Summing with 14 or 12? Summing with 14. So we just check 14. That's going to give us 19 here. Similarly here, we check the maximum, summing 14 or 13, which is 14. So it gives us here 23. And 13 plus 3 just gives us 16, and it's here. So, okay, so this is then the result of the problem, right? So we have here 20, 19, 23, which is the final result, and 16, right? So in this case here, the path is very clear, right? You just go from 23 to 14 to 10 to 3, which is similarly to what we have here in this triangle matrix, right? 9, 4, 7, 3. It's the same sum, right? So these are partial sums. This path represents partial sums to the result problem that we have, right? And then this gives us this structure of what the problem is about. Okay, so there are 3 rules to solve this dynamic programming matrix. First, if the column is 0, if it's the first column, we just check the row before, right? So we just check the row above. Okay, so for example, 10, I'm just going to check 3 here. If it's the last position in the row, so for example, 16, we're just going to check the previous row and the previous column. So we're just going to check in the up left diagonal. Otherwise, we're just going to get the maximum between the position above or the position to the up left diagonal, right? So it's the cases here that we checked the maximum. So with this rule, then we can create an algorithm that will explore and fill this matrix by summing it up. Once we have the final row filled, we can just check what is the maximum value in this row, and this should be the answer to our problem. Right, so let's give it a try to this problem. Let's just create here a Python package, problem 18. Okay, let's just create problem 18. And then we create here the file problem 18, okay? And then here, let's just start then with this smaller matrix first, okay? And as we go up, as we solve the problem, we put the other one. So I'm gonna put it here as a string, okay? This should be it. First, I need to convert this string into a number, right? A matrix of numbers, not of a matrix of strings. So I can first split this by the line break, and then I can convert it into for row in matrix. I can split by the space. And I can do the same thing here, another list comprehension here for column in the row. I can just convert it into, oh, of course not, because I need to do this, right? That should do it. Yes, exactly. So if we print this matrix now, it should be a matrix of numbers, right? So let's just check it. Problem 18. Yes, so we have 3, 7, 4, 2, 4, 6, 8, 5, 9, 3, which is how our matrix should look like, right? Okay, so now we can start iterating through this matrix. Okay, so we can go for row in range 1 to the length of our matrix. We're going to start from row number 1 because row number 0 is just 3. There's nothing we can do here. We just start from the second row, right? Row numbered from 1 onwards, and then we're going to check the columns. So for column in range, then we just have to check up to the size of the matrix. Okay, and then we check the 3 conditions that we talked about in here. The first condition is if j is equal to 0, right? So if our column is 0, so if column is 0, our matrix in the position row and the position column, I call like this, so I have to use this variable now. We're going to sum it with the previous row and in the same column. Okay. Otherwise, if the column is equal to the length of the matrix in the position row minus 1, right? So if we check if we are in the last position of that row, then it's the second condition here that we talked about, right? So we need to get that the matrix in the row and column position will be summed with the matrix in the row minus 1, column minus 1. Otherwise, then we are in the last condition, in which we have to check the maximum between the two adjacent positions. So here we have row, column is you sum with the max between the matrix in row minus 1, column minus 1, and matrix row minus 1, column. Right? This should do the trick for this problem. Then we have then the matrix with the final solution. That's still not the final result. Okay, the final result shall be given by the sum of the matrix in the last row, right? So if we get the matrix in the last row, we have to sum. Sorry, not sum. We have to get the maximum result in there. Right, so let's give it a try here. And the maximum is 23. This is how our matrix look like, which is exactly the same as we have here. And the result is 23, which is the same result here. Okay. So we have the solution to the problem. Let's test it to the bigger triangle. Okay, so let's just paste this bigger triangle here. And let's hope for the best. Let's go to solve the problem. And it's really fast, instantaneous. We have the solution here, 1074. I hope this is the right solution. Let's give it a try. Check. And it's right. So this is the solution to the problem, right? So it's a dynamic programming solution, not very large. Again, this is a n-squared solution, right? So with respect to the number of rows in the worst case scenario, right? So it's a not very complex solution, and it's a suitable solution to this problem.